Okay, yeah. So we mostly worked on 3D massive gravity. So I'll be talk about the 3D massive gravity examples. This is based on my recent paper with collaboration with Dr. Shailesh Kulkarni at SPPU, which published in Journal of High Energy Physics. So I planned my talk in three stages. So I'll talk about a little bit, introduce the symmetry algebra and groups, because we want to explain about the near horizon symmetries. Then we'll talk about a transition from our usual symmetry to the asymptotic symmetry, which is the main theme of the paper. And then the asymptotic symmetry, how it applies to the black hole CFT correspondence and its extension, which is the main work of our paper. Okay, fine. So about symmetry and symmetry algebra. So the fundamental equations of nature encapsulating the different physics has many classes of symmetries, as we know of, and that drives most of the 20th century theoretical research and has a very profound mathematical development and consequences in physics. And these symmetries and observed facts that dictates those symmetries gives us understanding why the things are the way they are. So about symmetry, according to Wigner, symmetry is like an operation or transformation that we perform to something and some objects, and that leaves that object or the equations or something invariant. We call that a symmetry. And neither she has a very great insight that if you have a continuous symmetry, that leads to a conservation law. In 1918 paper, Neither gave us a great insight. And these symmetries, conservation law, are intricately connected, and they are associated with continuous symmetries mostly, like translation in space. If we have a translation symmetry in space, linear momentum is conserved. Similarly, for rotational symmetry, we have angular momentum conservation and translation in time, energy conservation. And there are other class of symmetries like gauge symmetries, where the charges are conserved charges and those kind of things. And these symmetries are connected with the generators. So the conserved quantities what we get as a generators, and from those generators we get some conserved charges we calculate. That's the whole idea. So as a warm up to orient towards that symmetry and generators and those ideas and groups, I will start with a very simple example of rotation, how a vector is rotated. If I have a vector r in a 3D along an axis, arbitrary axis n, at a finite angle phi, then the finite rotation formula, as we see in classical mechanics, is given by this formula, which is the typical finite rotation formula we know from our study of classical mechanics. Now, this formula we can think of as an operation of a matrix, which is called the rotation matrix, over that vector r. So the application of rotation matrix rotates the vector r to some r prime direction. And if we take an infinitesimal change of that vector under the rotation, if the angle is very small, infinitesimal parameter, then the infinitesimal change we can calculate very simply from this formula is given by this, which we think of some matrix omega acting on R, where we can check that omega will be an antisymmetric matrix simply. And any antisymmetric matrix we can write in terms of our purely antisymmetric tensor in 3 dimension, which is the Levi-Civita symbol. In terms of Levi-Civita symbol, we get some matrix like M times N in this way, and these M's are called the infinitesimal generators of those rotations. So these are the generators, and if we calculate their commutators from those generators, we get an commutator algebra, which is given by this, which is usual angular momentum algebra simply. So these algebra, these are called Lie groups because these parameters are continuous, and if we continuously change those parameters, we get the different elements of that group. And our elements of this rotation group are those rotation matrices. These are the representations of those groups, typically speaking. Rotations are abstract elements. And those representations we got by exponentiating these generators from that group. And this is called the SO3 group because S is for the determinant is +1, is orthogonal group. And there are some connections with some universal covering group with SU2 and those things, which is a unitary group in 2 dimension. So these are the typical idea we get from classical mechanics about rotation. So summing up the lessons, what we get from here, which we use throughout this talk, is that we have some symmetry operations. Those symmetry operations, from that we get some generators, symmetry generators, and those generators algebra, we get the symmetry algebra, and exponentiating that algebra we get a group. So the crystallized wisdom is the Lie group, is like the exponentiation of Lie algebra in a very crude way we can speak. So this is the main theme. This is, we will walk and we get at different level. So now we come to the symmetry to asymptotic symmetry section. So as Minkowski said, the space-time, about the space-time symmetry, the Einstein's profound insight is that space of itself and time of itself will sink into mere shadows, and only a kind of union between them survive. So the symmetry operations in space-time is the general of symmetry transformations, which is called the space-time translation or a Poincare transformation. And these xa are the 4 vectors in our spatial relativity, and lambda ab are nothing but the generalized Lorentz transformation matrices. And if we talk about the symmetry generators in the same line, they will be 4 momentum and the generalization of those angular momentum, which is generalized angular momentum. And if you calculate the commutator algebra among them, you will get this algebra in terms of Minkowski metric eta ab, which is called the Poincare algebra. And the symmetry group will be a Poincare group, and its universal covering group will be R4 cross SL2, C. So in the same line of the rotation, we get a similar understanding of space-time symmetry in spatial relativity. We can think of spatial relativity in that way. Similarly, we can go further and go to the symmetry in geometry, which is Einstein's second insight about the general relativity, where we have the geometry of space-time is related by a metric tensor, which is a solution of Einstein's equation. And if we have a cyclic coordinate in that metric, that is a symmetry, and that is associated with the existence of Killing isometries or Killing vectors. And those Killing vectors satisfy some equations which we call a Killing equation. And these Killing vectors may be a global isometry, which is throughout valid in the space-time, or can be a gauge isometry, which is dependent on each point in the event, in the space-time. So these are the typical understanding of our symmetry in the context of general relativity, if we go translate that same idea. Now, in that context, there are some spaces which possess the maximal number of these symmetries, which we call the maximally symmetric spaces, which are both homogeneous, isotropic, and there are a limit. If I have a d-dimensional manifold, the maximum number of Killing vectors that is possible is d into d plus 1 by 2, that can be calculated from general relativity. And these are a typical example of that, which we use in theoretical physics, is ADS3 space, ADS space in 3 dimensions, which is a solution of this action, where R is the Ricci scalar and lambda is the cosmological constant. And for ADS3, the cosmological constant will be negative and given by minus 1 by L square, where L is the ADS radius, which is a solution of this. And these spaces, as they have Killing vectors or Killing isometries, have a symmetry group generated by those Killing isometries. Their symmetry group is SO2, 2. And the generators are, there are 6 generators because it is ADS3, and you can calculate the number of generators from d into d plus 1 by 2, that will be 6. And those generators are given by this relation, JAB is equal to XAXB. X is the position, and del A is like the moment. It's like some momentum kind of thing. And those symmetries, those generators generate the rotation and all those stuff in that space. So each and every geometry possesses this kind of symmetry group, and there are corresponding generators. Okay, now we switch a gear a little bit and we go to the CFT, which is the conformal field theory. We will talk about the 2-dimensional CFT in a very short span. So there are transformations which we call a scaling transformation, which makes the metric invariant under a scaling factor. So if we transform the metric from one coordinate to another, that metric just scaled up by some scaling parameter, which is called a conformal factor, and this is called a conformal transformation. And there are some transformations which we make in the coordinates. We go from xa to some xa plus xia, where these xia's are the generators of those conformal transformation. Then there are some conditions for which that matrix remains invariant, or the space-time does not change, or it remains conformally invariant, strictly speaking. And that criterion is, if we calculate for 2-dimensional conformal field theory, that is nothing but our Cauchy-Riemann condition in complex analysis. So actually those generators which actually generates those transformations are nothing but analytic functions. And if we calculate the generator algebra of those generators, we get some algebra which is known as d phase 1 algebra, and the corresponding conformal group will be the Mobius group in the similar line of thoughts. And if we extend that algebra to some quantum level, that algebra will be extended Virasoro algebra with some central term, where C is the central term. So this is a typical understanding of a conformal field theory in 2 dimensions. Now I will come to the main aspect of it, which is asymptotic symmetry. That is a comprehensive approach defining symmetries and associated conserved quantities in generic spacetime involved some introduction to boundary conditions. And those boundary conditions, in those boundary conditions, we apply a linearized theory. And in that reference, we take a reference background which admits several Killing vectors, but those Killing vectors actually satisfy Killing equations in an asymptotic limit. So these isometry are asymptotically defined and relevant, but not relevant globally. So these are kind of symmetries which we call the asymptotic symmetries. And the great insight comes from ADS-CFT correspondence is that the asymptotic symmetries of ADS-T spacetime in gravity is associated with the symmetries of conformal field theory. So my work now about my work, the first lesson comes from our earlier work is that the asymptotic symmetry algebra of black holes in ADS-T spacetime is related to the symmetry algebra of CFT2, which is the great pioneering work by Brown and Hanno in 1986. Another lesson comes from Strominger in 1998 is that for BTZ black hole, if we have the Virasoro algebra, they have calculated the central charges, which is 3L by 2G, and from that they have calculated microscopic black hole entropy from a very microscopic origin. Then Strominger give a great work about the Kerr CFT correspondence, where they have the Kerr metric, which has an isometric group, which is SL2, R cross U1, and the asymptotic analysis gives you the fall of conditions, which is given by this order fall of conditions given by Strominger, and it satisfies the d phase 1 algebra. And the canonical charges. Okay, 1 minute. Yeah, 1 or 2. Yeah. So canonical charge algebra will be given by this, and the canonical charge Strominger calculated is 12 J. J is the angular momentum, and it gives a chiral CFT because they have calculated only one algebra, because there are different modes, left and right modes, but they get only one algebra. Now for Einstein gravity, Azeyanagi showed in 2011 that for Einstein gravity for BTZ black hole, one can have a non-chiral extension. That means we get a 2 set of algebras rather than 1 set of algebras at the horizon. So our question is that, is it possible to get a similar result for the higher derivative theories of gravity rather than Einstein gravity? So we search for 2 higher gravity, new massive gravity and topologically massive gravity given by these actions. And we say that they have the same isometry. So we do a near horizon analysis of that theories, and the d phase 1 algebra give us the central extension terms. But we see that one of the central extension is 0, another is non-zero, one is 0. And we see that the issue is due to the boundary surface is null. So what we did, the remedy is we deform the geometry. And we give a deformation prescription, which we deform the geometry, and we see that the isometries are preserved for the deformation, and we get 2 centrally extended algebras with 2 central charges, which are both are non-zero, for both for NMG and both for TMG. This is the work we have done, and that central charge exactly matches with the spatial infinity central charges given by Brown and Hanno work. But we get for the near horizon analysis, and we see that the Brown-Hanno's asymptotic symmetry generators are exactly connected to our deformed asymptotic generator by a coordinate transformation that we see. Okay, thank you.
Any questions?
Okay, so the kind of 2 gravity, can you go to that slide, the PTG? Yeah. So there was TG, 2 gravity.
Okay.
Models
Yes.
Yeah.
New massive
gravity and topologically massive gravity.
Yes.
Can you explain what they are?
New massive gravity is if you have Einstein gravity, we have Ricci scalar as the action in the Einstein-Hilbert action, And if we introduce a cosmological constant like ADS space or some other spaces, maximally symmetric spaces, so we have cosmological constant in that parameter. Now, for new massive gravity, we have some terms like RAB, which is higher order terms. So it's like in the Lovelock model, we have different terms and we can constrain those terms. So there are RAB term, RABCD kind of terms. Those kind of scalars we can introduce in that. So new massive gravity is an extension of that Einstein gravity, beyond Einstein gravity, which have some higher curvature terms, but that is dominated by that 1 by m square factor, mass factor. So they are only relevant in very high energies. And similarly, this is mass of the graviton present. That's mass of the graviton that's present, because this admits graviton, propagation of gravity, massive graviton. And TMG is there is Chern-Simons term in Chern-Simons theory. Those Chern-Simons, if we add in the Einstein-Hilbert action, the Chern-Simons term in the action, that makes the topologically massive gravity. And actually, new massive gravity comes after topologically massive gravity as a parity even counterparts, something like that.
A lot of questions are rising in my mind, but first of all, I will make a comment.
Okay.
First 6-7 minutes you have spent only those known things. Groups are generators, groups are
true.
That's why coming to your own work, you get very less time.
Yeah.
And
so
there you fast you are moving well.
So actually, I thought there will be undergraduate students, so I start with a little bit basic things.
Oh, but tell me one thing that I lost you actually. There is we talked about the conformal field theory, and that is in 2D, right? And
yes.
What is that scaling goes in your own formulation of the what is that scaling? Yeah, that's true. I mean, 2D conformal.
So what we did, we didn't do conformal field theory. What we do with analysis was purely from the gravity side. So we get the algebra from the gravity side, and when we get the algebra, we calculated the asymptotic charges, and we get the charge algebra. And when we get the charge algebra, we see that those algebra is nothing but the algebra of some conformal group already exists. So in conformal field theory, there are some conformal group exist whose algebra we know from previous background. No, before 4D, there is nothing called that kind of correspondence. Like ADS3 CFT2 correspondence not exist in 4D. That's why it is a difficult. But we actually want that, but that is not exist. So we don't know.
Somewhere the scaling will come in actually. Somewhere that scaling will come in. Say for instance, the particle physics
True. I think maybe the scaling is coming from that because if we see the central charges, these central charges actually 3L by 2G. If we go to the natural unit, but in general unit it is 3L by 2LP, like Planck length. So that means there are ADS radius and there are Planck length. So Planck length to ADS radius, maybe there is a scaling. That may be a possible reason. Okay. Yeah.
What is Lie group and Lie algebra?
Okay, Lie group is Lie group is a continuous group which parameterized by some continuous parameters like angle. So if I am in a 2-dimension, I can rotate a disk. So those rotations from one point to another, they are parameterized by one parameter theta. That theta gives you different elements or different rotations. So if we take those rotations, so if we compose one rotation with another, that gives another rotation. So these becomes the elements of that group, and as it is continuous parameters, we can differentiate with respect to those parameters. So that's why it is continuous. So that's why it is called a Lie group, because it is continuous group in that sense. And it is another reason is that if we differentiate, we get the generators of those groups, which generates those groups, and they satisfy some algebra, which is bilinear and antisymmetric, and satisfy Jacobi identity, which is called a Lie algebra. And if we exponentiate those generators, we get the group elements. So in those connections, this forms what is called a Lie group in mathematics. Yes. SL2R. Okay, that is a special kind of group. That is the group of actually the covering group of Lorentz transformation. There is SL2R, SL2 comma, SL2R, spatial linear. S is for spatial, L is for linear, spatial linear group. Generators of SL2 comma R. Okay. Generators of SL2 comma R actually is this conformal group generator. So in conformal group we have different generators. Just a minute. CFT2, and those conformal group generators are actually generates those SL2 comma R generators actually. So there are rotations, dilations, spatial conformal transformations, and those things. So they generates Moebius group, and from Moebius group we can associate the generators with those SL2 comma R. Yeah. Okay, canonical charge algebra is that for first we get the generators. Now, when we get generators, we can calculate, integrate those generators and calculate charges. As we get in momentum, we get generators, and then you can integrate over the, or in normal trace energy momentum tensor, you integrate the 0,0 component and get energy, and ij component and get other momentums and other charges, trace energy momentum tensor. So by integrating those quantities, we get the charges, and those charges also depends on those generators I, and they satisfy a bigger class of algebra. That is the canonical charge algebra.
Charges are actually the parameters of the system.
Generator is generator. Exactly.
Something tau is alpha. That alpha is the charge. Tau is the generator.
Yes, yes, true.
So we don't have time for any more questions.
Yeah.
Thank you.
Thank you, sir.